Swayam Prabha. Digital India. Educated India.
Good morning to all of you. So, till the last class we had completed the analysis which we usually use for the mixed flow patterns, the transitional flow patterns and so on. We had dealt with the homogeneous flow model and we had also dealt with the drift flux model. Okay. So, today we are going to start the separated flow model, or in other words it is better coined as the two fluid model. Okay. In this particular model, exactly what we do is, this is usually applied for when we are having two phases and the two phases they are separated by a distinct interface. This can also be applied to mixed flow patterns as well. Okay. Here the basic thing which we do is, we consider each phase separately and we write down the equations of continuity, momentum and energy for phase 1 and for phase 2. And then we consider, in these particular equations itself, we consider the interaction between the two phases. Okay. So, therefore, for example, suppose we are considering say two phases flowing as separated flow in a particular channel. So, in that particular case I will just show you a figure. So, if this figure you see, there is phase 1 on the top and there is phase 2 at the bottom. So, basically suppose it would have been a single phase flow, then this particular fluid it would have interacted with the wall. Now, since there are two phases, therefore, each particular phase, say phase 2, that interacts with the wall with a wall shear stress which is tau W2, and it also interacts with the other fluid, and where the interfacial shear between the two is tau I. Okay. Now, this tau I, this has been wrongly written down in this particular case. Now, this sorry, no, it is correct. If the direction of flow is in this particular direction, then we find that naturally the interfacial shear will be opposite to the direction of motion. Now, since the direction of motion it takes place from the left hand side to the right hand side. So, naturally tau I will be in the opposite direction for the faster flowing fluid and in the direction of motion for the slower flowing liquid or the slower flowing fluid. Okay. So, therefore, in this case what we do, we consider the two phases separately. Say we consider phase 2 and then we consider phase 1. For each particular phase what we do, we write down the momentum equation, we write down the equation of continuity, we write down the energy equation. When we are doing this, then in that case we have to consider the interaction between the two phases. Okay. We have to consider that the two phases they interact and actually they will be interacting at the interface. Now, remember one thing, this is a situation for a completely separated stratified flow situation. So, therefore, the interface the interfacial shear it operates at a well defined interface, where the interface is well defined between the two phases. Suppose the other phase would have been distributed as bubbles or as slugs, Taylor bubbles, etc., etc., then in that case also the same concept can be applied. That is why we had applied the same concept in the drift flux model in order to arrive at a proper expression of F12, the interacting force at the interface. From there we tried to get some sort of a relationship between J12 and the input parameters. So, the only thing which is going to vary when the two phases are not so well separated is the area over which tau I is going to act and the magnitude of tau I as well. Okay. So, in this particular case it is pretty straightforward, and evaluating SI, the interfacial wetted perimeter along which tau I is acting. So, this is much straightforward in this particular case. It will be much more complicated in when the two phases are mixed together. But anyhow, the two fluid model is the most fundamental model. I should have started with this earlier, but I did not do this because I wanted to go stepwise. Okay. So, therefore, naturally the first thing was consider the two fluids to be completely mixed, and then you apply the mass momentum energy balance or the equations of continuity, momentum and energy across this particular two fluid, the mixture of the two fluids, and then you work accordingly. The other extreme is you consider the two phases to be completely separated, consider each phase separately, apply the equations. So, in the homogeneous model we had 3 equations, in this case we will be having 6 equations. Apart from having 6 equations, remember that we got to include the interaction terms in the constitutive equations. Now, how complicated this interaction terms will be, that will govern on how complex the model will be and how accurate it will be for practical purposes. Okay? But this is the actual, the most complex or rather the accurate way of modeling two phase flows, but we do not use this. The advantages and disadvantages we will be discussing shortly regarding this. So, naturally what are the main features, as I have told you, that we consider the two phases separately and we formulate separate mass, momentum and energy balance equations for either of the phases. Now, remember one thing, the main difference between single phase and two phase flows are the interaction terms. All these balance equations, they must contain the interaction terms which incorporate the transfer of mass, momentum and energy from the interface to the ith phase. This is something very important that we must be considering, both the, or rather we must be considering the interaction terms. If we do not consider the interaction terms, then naturally this simply becomes the single phase flow equations. Now, due to this, the separated flow model is more complicated than the drift flux model. Okay. This complicacy arises not only in the number of field equations. There we had 4 equations, as I have told you, here we have 6 equations, but this is not the only reason why two fluid model is more complicated than the your drift flux model. The main reason is that in this particular case we consider rather the necessary constitutive relationships which have to be incorporated in order to account for the interaction between the two phases. This is what is important. First is the number of equations have become more, and secondly the constitutive relationships which have to be incorporated in order to account for the interaction between the two phases. Okay. And this is particularly this is applicable when the degree of coupling is, or rather the degree of coupling, it is not very high. Under that conditions, this particular model is particularly applicable. When the degree of coupling is very high, then finding out tau I, finding out SI, they become much more complicated. Okay, if you see this particular figure, we find that finding tau I and SI becomes much more complicated when the degree of coupling becomes very high. In that case, the constitutive equations, they become much more complicated, and the accuracy of the constitutive equations, they govern the usefulness of this particular model. So, if those equations become very complex, then naturally this particular model will have very limited applicability. Okay. So, this is the thing. Now, the advantages you have over the drift flux model. Now, in this particular case, so it is quite evident that the interaction terms, they determine the degree of coupling, and therefore, they determine the transfer processes in each phase. Now, if these interfacial exchanges would not have been incorporated in the balance equation, then the two phases would have been essentially independent and they could be analyzed by mere single phase flow equations. When we start the analysis, we will find that the only difference between single phase flow equations and the two fluid model equations are the interaction terms. Okay. Now, when we should use it and when we should prefer the drift flux model. So, the advantages which we have over the drift flux model. The first thing is, it is more useful when the two phases are weakly coupled and the inertia of each phase, it changes rapidly. This is the first thing. When for weak coupling between the phases, when the inertia of each phase, they change rapidly. Under this condition, finding out tau I SI is not very difficult, and definitely under this particular condition, it is easier to use the two fluid model as compared to the drift flux model. Okay, because under when there is weak coupling, then finding out J21 becomes much more complex. So under those conditions we would prefer this. Next is due to the separate conservation equations. So, therefore, since we are writing separate equations for phase 1, separate equations for phase 2. So, therefore, what we do, it can predict more detailed changes and more detailed phase interactions as compared to the drift flux model. And it can also account for the dynamic and non-equilibrium interaction between the phases. And this is particularly useful for the analysis of transient phenomena, local wave propagation and related stability problems, as well as for flow regime transitions. Okay. So, therefore, we find that this particular model, it is particularly useful for the analysis of transient phenomena, local wave propagation and related stability problems, as well as flow regime transition cases. And when we are having a general 3-dimensional flow, naturally under that condition the 2 fluid model is going to be much better than the mixture model. Why? Because for really 3-dimensional cases, it is extremely difficult to develop the relative velocity correlation in a general 3-dimensional form, isn't it? See, whenever we were trying to derive the drift flux model, we had derived it for the 1-dimensional case, and then what we did, we incorporated C0 to account for the 3-dimensional case, with the supposition that C0 is not far removed from unity. That was when will it not be far removed from unity? When more or less the 2 phases, they obey the 1-dimensional flow assumption. Maybe there is a slight velocity or a voidage profile which can be accounted for. But if there is really very remarkable 3D effects, then naturally C0 will be far removed from unity, and then it is no longer a correction factor, isn't it? Then we have to do a proper balance and then find out a proper C0. Under that circumstance, it is much more easier to consider the 2 fluids separately and write down the equations, find out the interaction terms and then do it accordingly. Okay. So, remember one thing, whenever the 2 phases are weakly coupled, whenever we have some transient phenomena, local wave propagation and things like that, whenever there are rapid changes in inertia of the 2 phases, and when we want to predict more detailed changes, okay, more detailed changes and phase interactions, when the flow is truly 3-dimensional, under such circumstances generally we prefer, or rather it is better to use the 2 fluid model. And under what circumstances we should be going for the drift flux model? When the total response is more important than the local behavior of the individual phases. Okay. Naturally, when the total response is important, then in that case writing it down for phase 1, writing it down for phase 2 and then adding the 2 and then finding out the mixture response, it is not worth. It is better that we find the mixture response directly, and there we work with 4 equations and we can predict the mixture properties or the mixture characteristics as a whole by just incorporating the relative velocity between the 2 phases. So, under that circumstances the drift flux model is going to be better. And the other thing, naturally, when there is a strong coupling between phases, in that case finding out tau I, Si, they become very complicated, and in such cases we would prefer to go for the drift flux model. So, when it is more of a mixed flow, see, you cannot definitely say that this is totally dispersed flow, this is totally separated flow. Under normal circumstances, for the range of flow conditions that we encounter in industries, there will always be a good amount of interaction. When the interaction is such that one phase tends to get completely mixed in the other phase, then we prefer to go for the drift flux model, because even when they are mixed also, there will always be a relative velocity between the phases. And if we just consider the relative velocity and modify the mixture equation, it is going to be better. Okay. But when we find that the interaction is not such that one phase mixes in the other, maybe the interface can be very much wavy, or maybe there are well defined cross sectional areas occupied by phase 1, well defined cross sectional areas occupied by phase 2. Even for the slug flow model also, maybe at times the 2 fluid model can be much more useful. So, depending upon the flow situation, you have to decide whether you will go for the 2 fluid model or whether you will go for the separated flow model. Okay. Now, if we go for the different equations, what is the simplest? The equation of continuity. Now, if we start writing the equation of continuity, or in fact the mass balance equations, we will first write, and more or less lot of things are written down here. but it is better that we derive those. So, what is the general continuity equation? See, we will first do it for phase 1 and then we will write it for phase 2. So, for phase 1 we will have a Navier-Stokes sort of a expression rho 1 into 1 minus alpha plus differential rho 1 into 1 minus alpha u 1. Let us do it like this. This is equal to S 1 2 plus S 1. Now, what is this S 1? This S 1 is external source of matter. Means suppose some particular amount of phase 1 is entering the channel other than the flow condition. Usually this term can be taken as 0. And what is S 1 2? This is known as a source turn, represents mass rate of phase change per unit volume. That means, this tells us the amount of mass which goes from phase 1 to phase 2 or vice versa as a result of phase change, as a result of mass transfer, it can be anything. And S 1, this is the external source of matter. If any amount of phase 1 comes from outside into this, usually under the conditions which we consider, S 1 can be taken as 0. Okay? And similarly, we can write it down for phase 2, it is going to be rho 2 alpha. It is better I put a bracket over here. Rho 2 alpha u 2, this is equal to minus S 1 2 plus S 2. Okay. This S 2 is again external source of matter, usually this is 0, usually this is taken as 0, and naturally this represents, as I have told you, it is a source term which represents the mass rate of phase change per unit volume. So, naturally if mass is moving from phase 2 to phase 1, so therefore, S 1 2 is positive, mass is entering, and S 1 2 is negative since mass is leaving. So, these signs they will be adjusted according to the situation. So, this is the most generalized 3-dimensional form of continuity equation, and it simplifies to several simpler equations under different conditions. For example, if we have steady state flow, what happens? For steady state flow, what do you expect is going to happen? Your del del t terms, these two terms, they should cancel out, and under that conditions we get, for steady state flow, what is the thing we get? It is delta rho 1 1 minus alpha u 1, this is equal to S 1 2 plus S 1, and here it is going to become rho 2 alpha u 2 minus S 1 2 plus S 2. Next, if each phase is incompressible, what do you expect? If each phase is incompressible, then what do you expect? Your mean density becomes constant, or in other words, your rho 1, rho 2, they are constant. So, they come out of this. Okay. So, from this particular equation, what we get, this rho 1 and rho 2, they will be coming out of this equation, is not it? So, under that condition, what type of continuity equation do you expect? It should be del into 1 minus alpha del t plus delta 1 minus alpha u 1 equals to minus S 1 2 plus S 2 by rho 1, sorry, yeah, rho 1 plus S 1, and this is going to be del alpha del t plus delta alpha u 2, this is equal to minus S 1 2 plus S 2 by rho 2, is not it? So, depending on the condition, if it is steady state flow you get this, if each phase is incompressible you get such a type of situation. Now, in this particular case if we say that there is no phase change, then what do you expect? Suppose there is no phase change, both the phases are incompressible and there is no phase change. Under that condition what do you expect? This particular, the right hand side they disappear off, S1 S2 are anyhow 0, is not it. So, the right hand part they disappear off, is not it, and under that circumstances what do you get? We get del alpha del t plus delta alpha u2 equals to 0, well 1 minus alpha del t plus delta 1 minus alpha u1, this is equal to 0. Got it? Next, suppose there is no phase change, incompressible and steady state, but there is change in area, then what do we get? Say suppose it is no phase change, steady state. So, naturally these terms they cancel out and change in area. For that particular circumstance what do you expect? Your yeah these become equal to 0, is not it, and if it is one dimensional, I forgot to write, steady state change in area one dimensional. So, in that case what do you get? Under such circumstances these two things they become d d z a alpha rho 2 u 2, this is naturally equal to d d z of w 2, or in other words equal to w dx dz. No, sorry, phase change, very sorry, phase change, steady state, change in area and one dimensional, is not it? This is the equation that is expected. Similarly, you can write down the equation for the the phase 1 as well. So, therefore, these were the different ways. I think I have got a slide for these also. So, this is the general equation of continuity. If you notice my PPT, you are going to see this is the general equation of continuity. Then for incompressible phases, we have just taken out the rho part, rho 1, rho 2 out, and we get this. And then after integration across the duct, what do you get? Once you integrate this across the duct, you take a one dimensional case and then you integrate it across the duct. This general particular thing, if it is for steady state and to integrate it, or rather unsteady state also, it is one dimensional flow and to integrate it across the duct, then in that case what do you get? You get an expression which is written down in this particular slide. Okay. Now, in this particular expression, if we add up the two expressions, we can do it if we add up the two expressions and then with some sort of manipulations we get the separated flow equation for the mixture. Now, let us see how to arrive at that. This particular equation was del del t rho 1 into 1 minus alpha a plus del del z rho 1 into 1 minus alpha u 1 a. This is equal to integral of S12 plus S1 dA, is not it? Similar way we can write del del t rho 2 alpha a plus del del z. This will be equal to integral of minus S12 plus S2 into dA. Okay. Now, in the integrated form, this is the case. Now, in this particular equation, if we add the two, and we consider that GTP, this is equal to rho 1 u1 1 minus alpha plus rho 2 u2 alpha. Yes or no? Okay, GTP, it is nothing but rho TP UTP. What is rho TP? Rho 1 1 minus alpha plus rho 2 alpha, UTP u1 plus u2, isn't it? So, therefore, GTP is something of this sort. So, in this integrated form, if we add each of them and if we substitute this, just do it and see what you are going to get. Simply do it and then you see what you are going to get in this particular situation. What we get here, we get rho 1 into 1 minus alpha plus rho 2 into alpha into A. Okay. So, therefore, here we get del del T of rho TPA, it is rho 1 1 minus alpha plus rho 2 alpha into A, and this part is nothing but rho TP into A. Okay. Plus this portion will be del del Z of rho 2 alpha u2 A plus this part. So, if we add this up, rho 1 into 1 minus alpha u1 A plus rho 2 alpha u2 A. So, the rho 1 u1 1 minus alpha plus this whole thing, this particular portion, this becomes GTP. So, therefore, this is GTP into A, isn't it? So, this will be equal to this S1 to S1 to they'll cancel out, S1 and S2 they are almost equal to 0. So, this becomes equal to 0. Is this part clear to you, or should I explain this part once more? Once more. Thing is, what we did first, we took up the continuity equation. Just if you see the notice the PPT, this was the equation of continuity. Okay. For one dimensional case, what we have? We simply have del del Z, because we have considered the direction of flow as Z. Okay. So, for one dimensional case, it becomes del del T rho 1 1 minus alpha plus del del Z into this. Okay. Now, if we integrate this one dimensional equation, on integrating, what do we get? Sorry. So, this is for incompressible fluids and leave that. So, if we integrate it, on integration we get something of this sort, okay, this equation and this equation. Now, if we add the two, what do we get? For this derivative of T, it is del del T rho 1 1 minus alpha A plus rho 2 alpha A. Okay. And what is this part? Rho 1 into 1 minus alpha plus rho 2 alpha, this is rho TP into A. Achha, then del del Z of rho 1 1 minus alpha u1 A plus rho 2 alpha u2 A. Fine. Now, we know rho 1 1 minus alpha u1 plus rho 2 alpha u2, this becomes GTP. Therefore, this particular term becomes GTP into A. If we add these two, S12 minus S12, they cancel out. S1, S2, I have already told that we never have external sources of matter entering. So, these cancels out. So, therefore, this plus this, finally, it gives this particular expression. This is the equation of continuity for the mixture. Agreed? Now, if we go for the momentum balance equation. Now, what is the principle of momentum balance? All of us know. It is simply the rate of creation of momentum, rate of momentum outflow minus inflow plus the amount of rate of momentum storage, and here there is a little mistake, it is sum of forces acting on the two. If I just correct it, plus rate of momentum, this will be, anyhow we will correct it later, leave it now. This will be storage, this has to be equal to the sum of the forces. There is a slight mistake here which we are going to correct. So, rate of creation of momentum is nothing but rate of momentum outflow minus rate of momentum inflow plus rate of momentum storage, and that is nothing but equal to the sum of forces acting on the control volume. What is my control volume? Control volume I had already shown here. This is my control volume. It comprises of a cross sectional area A and a small length of the flow passage delta Z. Okay. So, therefore, this is the control volume. Now, in this particular control volume, what are the forces that are acting? Can you tell me? Pressure forces. in this direction it is P, here what it is P plus dP, or in other words what is this dP? Del P del Z into delta Z, isn't it? So, there is a pressure force acting. What else is acting here? Wall shear. So, there is going to be tau W2 into your wetted perimeter or the perimeter which is in contact with phase 2. Then there is tau W1 into the perimeter in contact with phase 1. Okay. So, therefore, 2 wall shear stresses will be coming, unlike 1 wall shear stress for single phase flows. And then there is one additional wall shear stress tau I. So, this tau I will also be coming in this particular case. Okay. In any other and of course, gravity is definitely there, the gravitational force. So, these are the total forces which will be acting. And what is the rate of momentum in minus rate of momentum out? So, therefore, we assume that W1 amount of fluid 1 is entering, W2 amount of fluid 2 is entering. Okay. And here what is happening? We assume the general case, some amount of change of phase takes place. Naturally, whenever we talk of change of phase, immediately it appears that maybe some amount of evaporation occurs, it can always be the reverse. So, if that is the case, then what happens? Some amount of say phase 1 it shifts to phase 2, say dW2 or dW1 whatever, that amount it shifts. Now, whenever that happens, there is also a momentum change. Why? Because some portion of the fluid which is undergoing change of phase, that actually changes its velocity from that of one phase to that of the other phase, since both the phases are flowing at different velocities. So, therefore, that also takes place. Okay. So, therefore, there is a change of momentum due to phase change as well. Fine. So, therefore, we will be equating, we will be writing down the total number of forces which are acting, then we will be writing down the momentum change, we will be equating it. We will be doing it once for phase 1, then for phase 2. And then if we add the 2, we will find we can combine it in different ways. If we add the 2, we will get the mixture momentum equation. Okay. So, let us do it and then let us see what we are going to get for this particular purpose. So, this is the momentum balance equation. Now, in this momentum balance equation, what is the rate of momentum, one dimensional flow? This is definitely we usually consider one dimensional flow. Now, if we refer to this figure, we find what is the rate of momentum outflow minus the rate of momentum inflow. This is naturally for phase 1. Okay. So, this is W1 U1 plus del del Z of W1 U1 into delta Z. Agreed? Minus W1 U1, sorry, minus W1 U1, okay, plus del del T of U1 rho 1 1 minus alpha A delta Z, where this is nothing but W1, okay, this part, this is W1. Okay. So, this is the rate of momentum outflow minus the rate of momentum inflow plus the rate of momentum storage here. Fine. And what is the rate of or in other words, this becomes, this is equal to delta Z into, just tell me if I make some mistakes. This is U1 square rho 1 1 minus alpha into A plus del del T U1 rho 1 1 minus alpha into A. Correct? Where how did we get this thing? This is W1 equals to U1 rho 1 1 minus alpha into A into U1. So, we have got this part. Is this portion clear to you? So, this is the rate of creation of momentum for phase 1. Agreed? This portion, is it clear to all of you? Okay. Now, what are the sum of forces? I believe I have the PPTs for this. On this control volume of phase 1, sum of forces acting on control volume for phase 1. What are the sum of forces? P into 1 minus alpha into A, fine, minus P into 1 minus alpha A plus del del Z of P into 1 minus alpha A delta Z. Agreed? Then this gives minus P delta Z del del Z of 1 minus alpha into A, to account for the force on the curved portion. Then of course, minus G rho 1 minus alpha A delta Z sin theta minus tau W 1 delta Z S 1 plus tau I P I delta Z. Sorry, S I, sorry, S I delta Z. See if this portion is clear to you. This is the force which is acting on one part, and then this portion is the force acting on the other portion. If you see this PPT, this is P and this is P plus dP. So, this is basically P plus dP, where we have written P plus dP as del del Z into P into 1 minus alpha into delta Z. Okay. And then this tau W2, sorry, tau W1, we are considering this particular phase, delta Z into S1, tau I SI delta Z, and of course, there is one particular force which is pressure force, which is acting on the curved surface area. Okay. So, therefore, the first two terms, if you take the first two terms, they refer to the pressure forces on the ends of the element. The third term, it is a pressure force on the curved surface, which occurs when there are changes in the cross sectional area only. Okay. Otherwise, this particular thing, it does not arise. Here I have not shown a change in the cross sectional area, but if this would have been a gradual expansion or a contraction, then naturally that particular force would have come. Okay. And this is naturally the gravitational force, and this is the shear stress forces, the wall shear stress and this shear stress. Now, if we equate this particular expression with this particular expression, then we get the momentum balance equation. Agreed? So, therefore, if we equate it, what do we get? On equating it, if you write it down and equate it, we get minus 1 minus alpha del P del Z minus G rho 1 minus alpha sin theta minus tau W 1 P sorry S 1 by A plus tau I S I by A. This will be equal to, this is going to be equal to del del T of rho 1 U 1 minus alpha plus 1 by A del del Z of W 1 U 1. This is the thing that we get for phase 1. Please do the derivations on your own, so that you are in a position to do it or to repeat it. So, this is the situation for phase 1 that we get. Similarly, for phase 2 also you can write such an identical thing. Write it down for phase 2. Just write it down for phase 2, let me see what you get. For phase 2, if you write it down, what do we get? I think it is already written down, so I will not bother to write it down once more. If you see the PPTs, more or less, rate of creation of momentum of phase 1, this is sum of forces acting on the phase 1, which I have said. You add it up, you get something of this sort. Then for phase 2 also you have the, you can have the similar type of equation. So, these are for one dimensional flow with everything else remaining. Okay. So, under steady state conditions, what do you get? Under steady state conditions, your this term and this term, they disappear off. Okay. So, therefore, under steady state condition, the equations it reduces to so you can write down the equation for phase 2 and then write down the corresponding, because usually we deal with steady state conditions. So, in steady state conditions we get my steady state and one dimensional conditions for one dimensional flow. Okay. So, this becomes minus 1 minus alpha dp dz minus g rho 1 1 minus alpha sin theta minus tau w 1 s 1 by a plus tau I s I by a, this is equal to d d z of w, or rather g 1 u 1, or in other words it is w 1 u 1 by a. In whatever form you can write it down, this is basically d d z of w 1 u 1 into 1 by a if we consider a to be constant. Okay. So, this is steady state conditions, one dimensional flow for phase 1. Fine. Similarly, for phase 2 also we can write down. Remember, all the deltas has become d's. Okay. Please remember these things, because these will be considered g rho 2 alpha sin theta minus tau I s I by a minus tau w 2 s 2 by a, this is equal to 1 by a d d z of w 2 u 2. Fine. Now, these are the two equations that we get. Both these two equations, and I have just written down the original form here. Cutting out these del del t terms, we can get this. Now, these two equations, they can be combined in several ways to give us the mixture momentum equation. One is you simply add them up. Okay. The other is if you subtract one equation from the other. So, what do we do? If we simply subtract, if we divide this particular equation with 1 minus alpha, we divide this particular equation with alpha, and then we subtract one equation from the other. What happens? This dp dz term, it cancels out, isn't it? Just do it and tell me what you are going to get. You divide one particular equation with 1 minus alpha and divide this equation with alpha, and then you subtract one equation from the other. Let us see what you get. We are expected to get something of this sort, rho 1 u 1 d u 1 d z minus rho 2 u 2 d u 2 d z. This will be equal to g sin theta rho 2 minus rho 1 minus your tau w 1 s 1 by a divided by 1 minus alpha. This can be taken as f w 1, the interaction of phase 1 with the wall, plus f w 2 by alpha. This f w 2 is nothing but tau w 2 s 2 by a, plus F12 by alpha into 1 minus alpha. Just see these two equations and see whether you can get what I have written down. Subtracting these two terms d dz of 1 by a, this particular term. Okay. This W2 is nothing but rho 2 U2 alpha into A. Okay. So, A cancels out. So, therefore, you get rho 2 U2 du2 dz, here rho 1 U1 du1 dz, you have subtracted the 2, then you have divided by alpha. So, alpha 1 minus alpha goes off. So, g sin theta into rho 2 minus rho 1. Okay. In the same way, if you do, you find that you get a equation something of this sort. Now, from this equation you find that it does not include the pressure gradient, and this can be considered as a relative motion equation. What does it do? It describes, if you see these two particular terms, you find they basically it describes the difference between the rates, describes the difference between the rates at which the two phases gain kinetic energy. See if you have understood what I have written down. Basically, if you find this is the difference between the rates at which the two phases gain kinetic energy, isn't it? So, this minus this, the rate at which they gain kinetic energy can be obtained from g sin theta rho 2 minus rho 1 minus the interaction of phase 1 with the wall by 1 minus alpha, the volume which is occupied by phase 1 plus the interaction of phase 2 with the wall divided by the volume occupied by phase 2 plus your interaction between the two phases by alpha into 1 minus alpha. This is one way of combining these two equations for steady state conditions which we have obtained. What is the other way? You simply add the two equations. Do the addition part and see what you get. You have just try to see, you get 1 minus alpha dp dz plus alpha dp dz. So, 1 minus alpha plus alpha, it gives you dp dz, isn't it? So, in that way you get dp dz. Here what do you get? G rho 1 1 minus alpha sin theta, g rho 2 alpha sin theta. It is simply g rho Tp sin theta. In this way, if you keep on adding each and every term, you finally get a mixture momentum equation which is of the same form that we had obtained for single phase flows, the same form that we had obtained for homogeneous flow model. It will be dp dz equal to one particular frictional term plus one particular gravitational term plus one particular acceleration term. Only thing is there the frictional term, it was just with the wall and nothing else. In this particular case, the frictional term will consist of phase 1 with wall, phase 2 with a wall, phase 1 and phase 2. So, just do this addition and then you see what you are going to get. Simply do this particular addition, and then the thing which we are going to get is it's minus dp dz equal to g sin theta into 1 minus alpha rho 1 plus alpha rho 2, or in other words this is rho Tp plus you get tau W1 S1 by A plus tau W2 S2 by A. We can also write it down as Fw1 plus Fw2, where this is Fw1, this is Fw2, which Fw1, Fw2 denoting the interaction of phase 1 and phase 2 with the wall, okay, plus 1 by A d dz of W1 U1 plus W2 U2. This is the acceleration pressure gradient. Okay. So, therefore, from here we get minus dp dz, this is minus dp dz gravitational plus your dp dz frictional plus dp dz acceleration. Okay. So, this is the final form which we get. Okay. So, what we basically did in this particular case, we first considered the two phases separately. We wrote down the momentum equation for phase 1, we wrote down the momentum equation for phase 2, and then we tried to combine them in different ways. In one particular way, we tried to combine them in such a way that they give us the rate or the difference between the rate at which the two phases gain kinetic energy, and the other one, a simple addition term. What we got a typical momentum balance equation for two phases when they are considered separately, that comprised of the gravitational pressure gradient, the frictional pressure gradient, and the acceleration pressure gradient. Remember, in the final expression there is no tau I here, because the two tau I's they cancel out, fluid 2 on fluid 1, fluid 1 on fluid 2, the two tau I's they cancel out. So, therefore, we do not have a tau I in this particular expression. Now, once we have got this particular expression, the next endeavor is how to find out the pressure gradient from it. Now, similarly, just as we had done in the previous case for homogeneous flow, we find that U1 it should be varying with Z. Why? Because the specific volume it varies, or the density it varies with the axial distance, just because of the pressure drop, isn't it? So, U1 it is going to be W1 by rho 1 A1 or rho 1 A alpha. So, we find alpha varies with Z, we find U1 varies with Z, A also may vary with Z. Okay. So, accordingly we have to write down this term, and then if we simplify the acceleration pressure gradient and we incorporate that particular term in the total pressure gradient, we would get the total expression comprising of a denominator and a numerator, where the denominator will give us the choked flow condition for two phase flow under separated flow conditions, and the numerator it will have 3 or 4 particular terms denoting the gravitational pressure gradient, the frictional pressure gradient, and the pressure gradient due to the area change and such other terms. Okay. So, in the next class we will be writing the particular momentum balance equation that we have got in this particular equation by substituting the acceleration pressure gradient, so that we get the final expression from where we can find out the pressure drop from known input parameters, and then we will try to define the condition of choking for two phases under separated flow conditions. So, that is all for today. Thank you very much.